It all started with a quiet announcement that many people almost ignored. While most tech headlines focused on faster gaming CPUs, AI performance, or benchmark records, AMD introduced something that could have an even bigger impact on the future of computing. Instead of only making processors more powerful, AMD is now focusing on making them much smarter and more efficient. This new direction has the potential to change the Linux ecosystem in ways many users don't yet realize. For decades, CPU development followed a simple formula. Every new generation aimed to increase clock speeds, add more cores, improve performance, and deliver higher benchmark scores. That strategy worked well for years, but eventually manufacturers reached physical and thermal limits. Increasing performance further also meant producing more heat and consuming more electricity, making it difficult to continue scaling processors the old way. At the same time, smartphones had already solved a similar challenge years ago. Mobile devices needed excellent battery life while still being capable of handling demanding tasks like gaming, photography, and video editing. Instead of using identical CPU cores, manufacturers introduced a mix of powerful cores for heavy workloads and efficient cores for everyday tasks. This approach dramatically improved battery life without sacrificing performance. The success of this hybrid design soon inspired the computer industry. Apple adopted the same concept with Apple Silicon, combining performance cores and efficiency cores into a single processor. The results surprised everyone. Apple laptops delivered incredible battery life while outperforming many traditional desktop processors. It proved that efficiency could be just as important as raw speed. Intel quickly followed by introducing its own hybrid processors featuring performance and efficient cores. Windows gradually adapted its scheduler to intelligently assign workloads between different core types. Linux developers also began updating the kernel to support these new architectures. Hybrid computing was no longer just a mobile technology, it had officially arrived on desktop and laptop computers. AMD, however, took a different approach for several years. Rather than mixing different core types, the company focused on continuously improving its successful Zen architecture. Every generation of Zen processors brought significant improvements in speed, efficiency, and overall performance. Combined with AMD's chiplet design, these processors became favorites among gamers, professionals, developers, and Linux users alike. Linux users especially appreciated AMD's growing commitment to open-source software. Graphics drivers became far more reliable, CPU support arrived quickly in the Linux kernel, and firmware updates became easier to manage. Compared to previous years, AMD built a strong reputation within the Linux community by working closely with open source developers instead of treating Linux as an afterthought. Now AMD appears ready for its next major evolution. Instead of relying entirely on identical Zen cores, the company is introducing low-power CPU cores designed specifically for lightweight workloads. These cores consume far less energy, generate less heat, and occupy much less space on the processor. While they are not meant to replace high-performance Zen cores, they are designed to work alongside them. Many people immediately assume that low-power cores mean slower computers, but that's actually a misunderstanding. Modern computers spend most of their time performing simple tasks like web browsing, checking email, syncing files, streaming music, running background applications, and handling operating system processes. These jobs don't require maximum processing power, making efficient cores the perfect solution. By allowing efficient cores to handle lightweight work, powerful Zen cores remain available whenever demanding applications need them. This means video editing, gaming, compiling software, or rendering projects can receive maximum performance without interference from dozens of background tasks. Ironically, using slower cores for simple jobs can actually make the entire system feel faster and more responsive. This is where Linux becomes especially interesting. Unlike proprietary operating systems that rely heavily on vendor-specific optimizations, Linux evolves through collaboration between hardware companies, kernel developers, enterprise organizations, and thousands of contributors around the world. Once support is added to the Linux kernel, nearly every Linux distribution can benefit from these improvements. At the heart of Linux lies one of its greatest strengths, the scheduler. The scheduler decides which applications run on which CPU cores, balancing performance, responsiveness, multitasking, and power efficiency. With hybrid processors, the scheduler becomes even more important because it must determine whether a workload belongs on a high-performance core or a low-power core. Fortunately, Linux developers have already gained valuable experience supporting Intel's hybrid processors. Years of work have improved Linux's ability to recognize different core types, monitor workload intensity, reduce unnecessary task switching, and optimize performance automatically. That means AMD's new hybrid architecture won't require Linux developers to start from scratch. Laptop users could be among the biggest winners of this transition. Battery life has traditionally been one of Linux's weaker areas compared to Windows or Mac OS, although recent improvements have significantly narrowed the gap. Efficient CPU cores could push Linux laptops to entirely new levels of endurance, allowing users to work longer without constantly searching for a charger. Lower power consumption also means less heat. Many modern laptops reduce CPU performance simply because temperatures become too high. If background tasks remain on efficient cores, high-performance cores stay cooler and can maintain higher boost frequencies for longer periods. The result is better sustained performance, quieter cooling fans, and a more comfortable user experience. Desktop users may think efficiency matters less because desktop computers are plugged into the wall, but that's not entirely true. Lower idle power consumption reduces electricity costs over time, especially for systems that remain powered on all day. Quieter fans, cooler components, and improved energy efficiency are benefits that every desktop user can appreciate. Software developers also stand to benefit enormously. Compiling large projects often uses every available CPU core, leaving little room for other applications. With hybrid processors, background tools like code editors, browsers, terminals, indexing services, and package managers can run on efficient cores while compilation uses the powerful Zen cores. This creates a smoother and more productive workflow. Virtualization is another area where Linux excels. Many developers and system administrators run multiple virtual machines simultaneously. Since many virtual machines spend much of their time idle, efficient cores can handle lightweight workloads while powerful cores remain available for demanding guests. This improves resource allocation while reducing energy consumption. The same advantage extends to containers. Modern cloud applications often consist of hundreds of lightweight services communicating with one another. Many of these services require very little processing power individually. Efficient cores can run monitoring tools, logging systems, and orchestration software while performance cores handle databases and demanding application workloads. Artificial intelligence is also becoming increasingly important. Although GPUs and dedicated AI accelerators perform most machine learning calculations, CPUs still coordinate scheduling, data preparation, memory management, and numerous supporting tasks. Efficient cores allow these background operations to continue without interfering with the processor's high-performance resources. Edge computing presents another exciting opportunity. Linux powers countless embedded devices, industrial systems, retail equipment, medical hardware, and transportation networks. These devices often operate under strict power limits while running continuously for years. Efficient CPU cores make it possible to process sensor data, communications, and monitoring tasks while reserving powerful cores for occasional heavy workloads. Home lab enthusiasts may appreciate this change just as much. Many Linux users build servers for media streaming, virtualization, home automation, Kubernetes clusters, and network storage. These systems often run 24 hours a day, making energy efficiency increasingly valuable. Even small reductions in power usage can produce meaningful savings over the course of a year. Gamers should also pay attention. Linux gaming has grown rapidly thanks to Proton and the Steam Deck. While games themselves benefit from powerful Zen cores, background software such as launchers, voice chat, streaming applications, browsers, and recording tools can move to efficient cores. This reduces competition for resources and creates a smoother overall gaming experience. Content creators stand to benefit in similar ways. Video editing, animation, music production, photography, and 3D rendering frequently involve multiple applications running simultaneously. Hybrid processors allow rendering tasks to occupy performance cores while previews, media indexing, synchronization, and communication software operate on efficient cores, improving responsiveness during creative work. There will certainly be challenges along the way. Some older software assumes that every CPU core offers identical performance. Benchmarking hybrid processors is also more complicated because results depend heavily on how effectively the operating system schedules workloads. Linux distributions will need continued testing and optimization to deliver the best possible experience. Fortunately, the Linux community has successfully handled major architectural transitions before. Support for multi-core processors, simultaneous multi-threading, NUMA systems, chiplet architectures, and hybrid CPUs all required significant engineering work. Over time, these technologies became seamless parts of the operating system, and most users never had to think about the complexity happening behind the scenes. AMD's strong relationship with the open-source community provides additional confidence. The company has steadily increased its cooperation with Linux developers by contributing documentation, improving driver support, assisting Mesa graphics development, and working closely with kernel maintainers. This collaborative approach should help hybrid processor support mature much more quickly than many people expect. Ultimately, AMD's new low-power CPU cores represent far more than another hardware feature. They signal a major shift in how processors are designed and how operating systems manage workloads. Instead of chasing maximum performance at all times, the future of computing is about using the right core for the right task. Linux, with its flexibility, open development model, and powerful scheduler, is perfectly positioned to benefit from this new era. If AMD's vision succeeds, this quiet architectural change could become one of the most important milestones in the future of Linux computing.